All right, hello everyone. Today we're going to start chapter 6, and this is going to revolve around the structures of covalent molecules. Before we can actually start talking about the structures of covalent molecules, there's one concept we need to introduce first, which is this idea of electronegativity and bond polarity. So if you remember, just to kind of rewind here, we talked about ionic compounds versus covalent compounds. And the main thing that we talked about thus far was the fact that we name them differently, right? So when we were talking about ionic, all these compounds, it was all about how to spot which one was which, because that leads to a different nomenclature scheme, right? So let's take, for example, NaCl compared to, I don't know, carbon dioxide, something like that, right? These two are named differently because one's an ionic compound and one's a covalent compound. And the way that we were taught to spot that really easily is because for sodium chloride, sodium lives on one side of the periodic table, whereas chlorine lives on the other side, right? So if one lives on the left and one lives on the right, it's an ionic compound. For CO2, both carbon and oxygen live on the right side of the periodic table. So that's how we were able to easily spot ionic versus covalent compounds. Okay. This chapter, we're predominantly going to be talking about covalent compounds. This particular concept of electronegativity applies to both. Okay, so it's this idea of looking at the electron distribution within a bond. So remember, if we had sodium chloride, we have a sodium ion which has a +1 charge, and a chlorine ion which has a -1 charge, right? And so the whole idea was that that sodium atom completely gave up that electron to that chlorine atom. Right, so we think about these as like two hard spheres being bound together by this opposites attract covalent, not covalent, I'm sorry, Coulombic force. On the other extreme, we have this covalent bond, which remember we said was a sharing of electrons. And so if we talk about what we're going to call a pure covalent bond, that is between two identical atoms. So for example, two chlorine atoms will bound to one another in a covalent bond where they're sharing a pair of electrons, okay? And important, the distribution of electrons is the same. So you have the same amount of electron density on each chlorine atom. All right, so now we're going to talk about a characteristic of covalent bonds that we haven't talked about before. And this is when you have covalent bonds between two different atoms. This is what we would call a polar covalent bond. And the reason why we call it a polar covalent bond is because the distribution of electrons is not shared equally in these two types of bonds. So let's look at kind of an extreme example, but nonetheless, HCl, where we have on the one hand, here's our chlorine atom, and on the one hand, here's our hydrogen atom. Um, the electrons within this covalent bond are not being shared equally. Chlorine is what we're going to learn about, what's called an electronegative atom. It likes to hoard electron density onto itself. So it's pulling electron density away from this hydrogen atom such that it has a little bit more of a negative charge. We represent that with this, like, it's this Greek letter, lowercase delta, and negative, and then the hydrogen has less electron density. Again, that same lowercase Greek letter delta with the positive sign. Okay, so what's really being represented here is electron density. So let's take a look at like the maps of electron density, see if we can't see what's up. Okay, so these are actually using this like fancy computer program that calculates where electrons are. If it's really red, it means that there's a lot of electrons. If it's blue, it means that there's not a lot of electrons. So this is our same three compounds here. Again, importantly, when we look at what we called our pure covalent compound, the distribution of electrons is perfectly symmetrical. Okay, they do tend to live a little bit at the ends there as opposed to in the very middle, but nonetheless, there's this perfectly symmetrical distribution of electrons. So that's what makes this pure covalent. Where we go to ionic, there is like this like stark cut in half difference between the positive end and the negative end, right? So this is the chlorine ion with its negative charge. This is the sodium ion with its positive charge. All right, so this was ionic. And then we have this polar covalent bond between HCl. So there's still this sharing of electrons going on. It's not that stark, clear-cut difference, but nonetheless, it's this very uneven sharing of electrons, right? So HCl, or in HCl, the chlorine atom has the vast majority of the electron density sitting on top of that, whereas the hydrogen atom doesn't. So again, that's how we sort of marked before. The chlorine has this partial negative charge, meaning it has more electrons sitting on top of it. The hydrogen has this partial positive charge, meaning it has more positive charge sitting on that. This is going to be something that's going to be important a little bit later in the chapter, but we need to learn it before we learn structures, because we're going to talk about the most electronegative versus the least electronegative atoms. So we need to be able to identify trends based on the periodic table. And indeed, that's exactly what it is. It's basically another one of these periodic trends where everything points towards fluorine. Okay. Fluorine is the most electronegative atom. So everything kind of like in terms of the periodic trends is pointed that way. This is what's called the Pauling electronegativity scale, named after a dude, Linus Pauling. You see every element's been given a number here. Let me use a distinct color. So fluorine, again, is the highest at 3.98. You go all the way to the other extreme end of things. You have like cesium at 0.79 and anywhere in between, right? So these numbers here correspond to the electronegativity of a particular element. So if we wanted to compare which one's more electronegative, boron or oxygen, look at their electronegativity value. You can see that oxygen is indeed more electronegative, okay? So anyways, this is this idea of electronegativity. And again, what it corresponds to is the propensity of an atom to hoard electron density, right? So we talked about comparing chlorine and hydrogen in HCl. We saw that chlorine had a significant amount of more electron density. That's because it has a higher electronegativity, right? So it has a propensity to hoard electron density onto itself compared to its less electronegative counterpart, hydrogen. Okay, and we can calculate the polarity in a bond, you know, kind of like assign a number to it by taking the difference, or rather the absolute value in the difference between electronegativity of the two atoms that are involved in a particular bond. Okay, so let's take a look at a few of the ones that we kind of already looked at. So first of all, we called Cl2 a pure covalent bond. So let's take a look at why that might be. We're going to take a look at the electronegativity of chlorine, 3.16, and we're going to take the difference between these two atoms. Since they're both chlorine atoms, that would be a difference in electronegativity of 1.36 minus 1.36, which would be 0. So since that difference in electronegativity is 0, that's why we call it a pure covalent. That's not how you spell that. Covalent compound, because it has a difference of electronegativity of 0, right? So there's no unequal distribution of electrons in that molecule. If we take a look at another one, we have HCl. That was our other example. And if we want to like quantify the polarity of that bond, we're going to take the difference in electronegativity between these two. And we're going to take the absolute value. It's always going to be a positive number. So hydrogen's 2.20 that came from over here, minus chlorine, which is the 3.16. Punch that into our calculator and we get 0.96. So that's somewhere kind of in here. All right, and this is what we called a polar covalent. Oops. Polar covalent bond. Actually, anything kind of in this region here above 0, we consider to be polar covalent. And then we can kind of talk about the degree of how polar that bond is by actually calculating the difference in electronegativity. So for example, we would say that the OH bond is more polar than the NH bond. And we can do that by calculating the difference in electronegativity for each. For oxygen, hydrogen, I have 3.44 minus 2.20. This would give us a value of 1.24. If we did the same thing for nitrogen, it would be 3.04 minus 2.20, which, if my mental math is right, would be 1.04. So we can see by performing that calculation that indeed the OH bond is more polar than the NH bond. Okay. So anyway, that's how we can actually quantify electronegativity. Our polarity within a bond is by calculating the difference in the electronegativity of the two atoms. Okay. Above that 1.7 range, that's what we call an ionic bond. So at that point, the electrons aren't even really being shared at all. They're really sitting directly on those. So notice how we even have, you could calculate the difference in electronegativity for an ionic bond as well, but it would sit in that different range above 1.7 difference. Okay. And again, anything, if it's 0, so basically the two atoms have to be identical, that would be a pure covalent bond. And again, what that means is that electrons are being shared perfectly evenly. If it's between 0 and 1.7, you have this unequal distribution of electrons. So one atom has more electron density on it than another atom. And above that 1.7, then it's an ionic bond, and that unequal distribution is like completely unequal. One atom has the electrons, the other one doesn't.